There is something deeply unsettling hidden within the laws of physics, something that challenges our basic understanding of reality. It is not a metaphor or a piece of science fiction, but a real prediction that comes directly from the equations governing the universe. When you hear about antimatter, it might sound like an exotic concept, but within the framework of physics, it has a very precise meaning. In fact, according to the interpretation developed by Richard Feynman, antimatter can be understood as ordinary matter moving backward through time. This is not poetic language. It emerges naturally from the mathematics used to describe how particles behave. The same equations that allow your electronic devices to function also suggest this strange possibility, forcing us to reconsider what time really means. To understand how this idea came about, we have to go back to a major problem faced by physicists in the early 20th century. A brilliant scientist named Paul Dirac was working on an equation that combined quantum mechanics with the theory of relativity developed by Albert Einstein. Dirac's equation was elegant and powerful, successfully describing the behavior of electrons. However, it came with a surprising and troubling implication. The mathematics did not allow for just one type of solution. Instead, it predicted that for every electron, there should exist another particle with the same mass but opposite charge. At first, this prediction seemed absurd. Physicists had never observed such a particle, and the idea of a mirror version of matter sounded almost like fantasy. Yet Dirac trusted the mathematics. He believed that if the equation was correct, then nature must contain these particles, even if they had not yet been detected. This was a bold stance, but history would soon prove him right. In 1932, an experimental physicist named Carl Anderson was studying cosmic rays using a device called a cloud chamber, which allows scientists to track the paths of charged particles. While examining the trails left behind, he observed something unusual. There was a particle that behaved exactly like an electron in terms of mass and motion, but its charge was positive instead of negative. This was the first observation of the positron, the antimatter counterpart of the electron. The discovery confirmed Dirac's prediction and marked a turning point in physics. Antimatter was not just a mathematical curiosity, it was real. Later, Feynman provided a deeper interpretation of these findings. By analyzing the equations, he showed that an antiparticle can be viewed as a normal particle traveling backward in time. This does not mean we see particles literally moving into the past, but rather that the equations describing their behavior can be interpreted in this way. This idea challenges our everyday intuition about time as something that only flows forward. In the world of quantum mechanics, the distinction between past and future is not always as clear as we imagine. The laws of physics at their deepest level appear to allow processes that can be interpreted in either direction. What seems like a violation of common sense is actually a reflection of how the universe truly operates, reminding us that reality is often far stranger than our intuition suggests. But it curved the wrong way in a magnetic field. It was the positive electron, the positron. Antimatter was real. But here is where the nightmare started. Physicists realized that when matter meets antimatter, they don't just bump into each other, they annihilate. They disappear completely, turning into pure energy, 100% efficiency. So we had a new problem. If the universe is made of math and the math says antimatter exists, how do we describe it without breaking physics? See, usually when we calculate how particles move, we look at their energy. Energy is supposed to be positive. You have energy or you don't. But the equations for antimatter kept spitting out something impossible. Negative energy. What does negative energy even mean? Does it mean less than nothing? If you have a ball with negative energy and you push it, does it move backward? The standard view of physics was collapsing. They tried to patch it up with complex ideas like the Dirac sea, imagining the universe as an infinite ocean of invisible particles. It was messy. It was ugly. Physics needed a savior. It needed someone who didn't care about the rules of how things should look. It needed someone who only cared about what worked. Enter Richard Feynman. Feynman was different. He didn't like complex philosophical patches. He liked pictures. He liked simplicity. In the 1940s, while working on what would become quantum electrodynamics, or QED, Feynman looked at this negative energy problem and he realized something profound. He looked at the math for an electron. Then he looked at the math for a pause. He realized that if you just flip the sign of time in the equation, The negative energy disappeared. Let me break this down, because this is the moment everything changed. Imagine you are watching a movie of a billiard ball rolling across a table. It moves from left to right. Now imagine you play that movie in reverse. The ball moves from right to left. In classical physics, that's just a rewind. But in quantum mechanics, Feynman argued that a particle moving forward in time with positive charge is mathematically identical to a particle moving backward in time with negative charge. This led to the famous Feynman diagrams. These little doodles won him the Nobel Prize. In these diagrams, time usually flows from the bottom of the page to the top. An electron is a straight line going up, but sometimes you see a line going down. To a normal person, that looks like a particle moving down. But to a physicist, a line pointing against the flow of time represents antimatter. Feynman was saying, stop worrying about negative energy in direct seas. Just treat the positron as an electron that is traveling back to the past. Think of it like this. Imagine you are looking at a road through a narrow slit in a fence. You can only see a tiny slice of the road. You see a car pass by going north. Then a few minutes later, you see a car going south. You think they are two different cars. But what if you could see the whole road? What if you realized it was the same car? It drove north, did a U-turn, and drove south. Feynman proposed that creation and annihilation of particles are just the U-turns in time. When an electron and a positron meet and explode into light, from a God's eye view outside of time, nothing was destroyed. The particle just hit a wall in time and bounced back. It changed direction. It stopped going to the future and started going to the past. This was the proof. The math worked perfectly. If you treat antimatter as time-reversed matter, all the paradoxes vanish. The equations become elegant. The universe makes sense again. But it opened the door to a thought so crazy, even Feynman was hesitant to say it out loud at first. There is a legendary story about this. It involves Feynman and his mentor, John Wheeler. One day, Wheeler calls Feynman on the phone. He's excited. He says, "Richard, I know why all electrons have the same charge and the same mass." Now stop and think about that. Why are all electrons identical? Every apple is different. Every person is different. But every single electron in the universe, from the ones in your brain to the ones in a star a billion light years away, is exactly 100% identical. They are clones. Why? Wheeler said, because they are all the same electron. The theory goes like this. Imagine the universe is a massive tapestry of time and space. There is only one electron, just one. It starts at the Big Bang, travels to the end of time, then it turns around. It travels backward in time all the way to the Big Bang. Then it turns around again, forward, backward, billions and trillions of times. It zips back and forth through history so many times that at any specific moment, like right now while you watch this video, that single electron crosses our slice of time trillions of times. When it crosses going forward, we see an electron. When it crosses going backward, we see a positron. Feynman loved this idea. It was wild, it was elegant, and it explained the cloning problem. Of course, Feynman, being the pragmatist, found a hole in it. He asked Wheeler, if this is true, there should be an equal number of electrons and positrons, but there aren't. There's way more matter than antimatter. Wheeler, never missing a beat, joked, maybe the positrons are hiding in the protons. While the one electron universe remains a theory, a beautiful unproven thought experiment, the core mechanism behind it is standard physics. The part about time reversal wasn't the joke. That part stuck. In the rigorous math of quantum field theory, which is the most precise theory humans have ever invented, the time reversal operation is crucial. You literally cannot do the math without it. We are forced to accept a strange idea when we study physics deeply. The difference between past and future is not as fixed as it feels in everyday life. In the microscopic world, time does not behave in the simple, one-directional way we experience. This leads to a natural question. If antimatter can be interpreted as matter moving backward in time, then why can't we use that fact to send messages into the past? Why can't we build some advanced machine and warn our earlier selves about mistakes before they happen? The answer lies in the difference between the tiny world of particles and the large world we live in. The interpretation developed by Richard Feynman shows that individual particles don't really feel time the way we do. An electron has no awareness of yesterday or tomorrow. It simply follows the mathematical rules that govern space and time. In those rules, processes can be described in ways that look like motion both forward and backward in time. But human beings are not single particles. We are incredibly complex systems made of trillions upon trillions of atoms, all interacting in chaotic ways. For a single particle, reversing direction in time is mathematically possible, but for an entire human body to do the same would require every atom to move in perfect coordination, retracing its exact path. The probability of that happening is so small that it is effectively zero. This is where the concept of entropy becomes important. Entropy is a measure of disorder, and in the universe, disorder tends to increase over time. That increase is what gives us the arrow of time, the feeling that time moves forward and never backward. However, there is a deeper and more unsettling implication hidden in this picture. If even a single particle can be described as traveling from the future to the past, then in some sense the future must already exist. You cannot come from a place that does not exist at all. This leads to the idea often called the block universe. In this view, past, present, and future are not separate things unfolding one after another. Instead, they all exist together as a single structure, like a frozen landscape. Our consciousness simply moves through it, experiencing one moment at a time. In this picture, we can imagine ourselves as being carried forward by the flow of entropy, moving steadily from past to future. Meanwhile, antimatter, in a certain interpretation, can be seen as moving in the opposite direction, like a current flowing upstream. It does not mean we can observe this directly in everyday life, but the mathematics suggests that the underlying structure of reality allows such descriptions. What this really shows is how unreliable our common sense can be when applied to the quantum world. We are used to thinking of time as a straight line, always moving forward, but physics tells us that reality is far more subtle. Concepts like forward and backward may not be as fundamental as we once believed. Instead, they may emerge from deeper laws that do not favor one direction over the other. So the next time you hear about antimatter, don't just think of it as something exotic or dangerous. Think of it as a clue, a hint that the universe is far stranger than our everyday experience suggests. It reminds us that the rules governing reality are not built around human intuition. They are built on mathematics. And those rules often reveal a universe that is far more mysterious and far more fascinating than we ever expected.